So, do you remember how last week I wrote a bunch of code and then said that I wasn't going to test it, but that it should be all straightened out by this week's video? I almost got away with it too. There's a small error in my matrix code that I wrote last week that is going to have to be fixed. There's also another small error that has apparently been lurking there since like a year ago that I haven't noticed until now, but it's very silly and doesn't actually affect collision code, and it may have spotted it on that in the demo scene window that I had up a minute ago, but we'll fix that too. And the error pertains to the matrix 3 get rotation matrix method, and the error in particular is that I have accidentally transposed each of the values here. So instead of saying like new matrix 4 self xx y x z x, we want these to be the other way around. So we want this to be a new matrix 4 self xx x y x z. And then on the middle row, yx, yy, yz, and then on the bottom row, zx, zy, zz, and like that doesn't affect like the game crashing or anything like that, but it does affect the rotations that things are like given when you try to go between a matrix 3 and a matrix 4. We like it when our data isn't being transposed randomly when you do operations like this. So we'll fix that real quick. I've also, in the intervening week, added myself a call test ob like object to the test like the test code, and a call test capsule object to the test code. The call test capsule is just going to be drawing like a capsule made of 2 spheres and a cylinder, and it's not very fancy. The call test ob is basically an axis aligned bounding box that has been given orientation. If you want to look through that, you can see that we are using the get orientation matrix method of a matrix 4 to go from a matrix 4 that we're generating for orientation and going to a matrix 3 for the actual shape data. And we've also got in the draw method down here, we're going the other way. So we're going from the 3x3 orientation matrix to a 4x4 world transform matrix, using the orientation axis as the rotation. And the consequence of having that error in the matrix 3 class was that things were not being rotated in, like things were not being drawn rotated in the same way that they were being stored as in the game. And rotations being different means that you could have some shapes that look like they're colliding when they're drawn, and they are not colliding like in the game's internal data structures. And the other error that I spoke of, how many of you noticed down here in like the UI overlay explaining which keys to hit to bring up which shapes, how many of you noticed that instead of saying like N shape 2 line, M shape 2 mesh, I had like the letter N for both of them? There's got to be at least one person who noticed that I apparently let that slip for an entire year. So I'm going to go and commit these 2 changes. This is just going to be, I've apparently got some stash changes. I don't know what those are. They're probably not important. Fixed some issues that I didn't notice last time. Was this like, oh, okay. I'm going to get rid of those. I apparently wrote out a bunch of like test classes and then like stashed them for some reason, and then I replaced them with new test classes and forgot about the stashed ones. Anyway, that may or may not inspire confidence in the rest of these videos, but we're going to move on. So, call obs. I'm going to be writing a bunch of code for checking call obs today. I'm going to definitely get to point, sphere, ab, and probably plane in this video. This is also going to require writing out some additional helper functions such as nearest point and get interval, those 2 old friends from separated axis theorem and from just generally checking the nearest point. And I'm going to also try and get through check ob and check triangle today. No guarantees on that depending on how long this video ends up taking. If I don't get to those today, I will get to those in next week's video when I talk about obs, rays, and lines, which shouldn't take very long anyway, because line is just going to basically be doing what we've done so often when it comes to lines, and doing like a mini raycast. So when it comes to checkpoint, we're going to start out by getting the direction vector from the position of the ob to the position of the point that we're checking. So that's going to be point dot position dot, that needs to be an equal sign, point dot position dot sub self dot position, and this is going to be our basically a direction vector that we check each of the axes of rotation against. And we're also going to make use of some of the as array methods that I wrote for the matrix and the vector last time. We're going to say, let's call it size array is going to be equal to self.size.asArray as linear array. And we're also going to have self.orientation array is going to be self.orientation.as vector array. So size array is going to be an array of 3 floats representing the components of our size, and orientation array is going to be an array of 3 vectors representing each of the columns in the matrix 3, so that's going to be the 3 axes of rotation. And to figure out if a point is contained within an AB, we are going to first loop over for I equals 0, I is less than 3, I plus plus. Loop over each of the vectors in the orientation array. Obligatory shout out to the magic number 3 that is in this for loop, unless you are planning on extending the system to use to do like collisions with 4-dimensional shapes or something like that. I don't think this is going to really pose a problem, but if it makes you happy, you can do like I is less than the array length of orientation array or something like that. Anyway. So we're going to loop over each axis of orientation. I'm going to shorthand this to var axis is going to be equal to orientation array index I. And we're going to, I suppose, project the direction vector onto each of these axes. So we can say var dist. So this is going to be the projected distance of the direction vector onto the axis that we're testing using the dot product. And that's going to... this gets the length of a particular vector on a particular axis. In the past, I've done this with things like planes and ABBs for like projecting a vector onto the X, Y, or Z axis. But you can do it with any axis. You can do it with any vector 3 representing an axis, as we are doing with the orientation. It doesn't have to be aligned to like the coordinate system. And we can say if the absolute value of the distance is greater than the absolute value of the axis, the size array index I, then return false. So if the distance from the AB to the point is greater than the OBB's size on that axis, that means that the point is farther away from the OBB than the the extent of the OBB, and there is no collision. Otherwise, the point will be within the OBB on that axis. And if none of the 3 iterations of this loop return false, then we can say return true. So if the distance from the OBB to the point on each of its 3 axes of rotation is not greater than the size of the OBB on that axis, then the point is contained. And we can run this and we can test this. Now that I've fixed that little matrix bug, hopefully we'll get the right answer. So if I were to bring myself up an OBB and if I were to move it around, you can see that if I were to move it just outside the point, and don't let the fact that the point as it's drawn here has volume fool you. These points are basically a 0-dimensional coordinate with 0 volume, or they're a 3D coordinate with 0 volume anyway. The fact that the point is kind of big, like a little sphere, is just there so that we can see with our eyes where it is. It's really the center of the point that you want to pay attention to when you're judging whether or not there's a collision. So we can move the OBB up or down, and we can see that when the OBB is about here, very briefly, there's collision. We can move the OBB side to side. We can generate another one, and we can see that when we move the OBB outside the bounds of the point, outside the center of the point anyway, then there stops being a collision. That's great. Okay. This is going to be checking OBBs and points for collision. Do I want to bring up that matrix, haha, pun matrix, of which collision shapes we've finished off? Like I had at the beginning of the series. I kind of want to. I might make it like a full piece of paper with all the shapes that I want to implement. So that'll be the existing shapes, OBBs, and capsules. Not sure if I want to do any other shapes beyond that. I think that'll be at least as far as primitive shapes go for this 3D collision series. So, for checking an OB against a sphere, we can do exactly the same thing for the OB sphere as we did with pretty much all of the other like sphere collisions. This one can be, for example, get the nearest point. So we can say nearest is going to be self.nearest point to the sphere dot position. We can say our dist is going to be nearest point dot distance to self dot position, and we can return true if the distance is less than or equal to the sphere dot radius. This isn't the hard part of checking an OB against a sphere. The hard part is going to be doing the nearest point method, and that is going to be implemented down here at the bottom. So the nearest point to an OB. So this is actually going to be a lot like the checkpoint method for an OB against a point. And I'm actually going to do this by copying and pasting a bunch of code and explaining the differences rather than writing out almost identical code twice. So we're going to start with, I'm just going to initialize a result up here at the top of nearest point. And result can be our self.position in space. So we're going to start at the OBS like position in space. And we're going to essentially trace out on each axis the closest point on each axis to the vector 3 that's being passed in as an input. An obvious change that we're going to have to make is that instead of saying var dir is point.position.sub, we're going to have to say just dir is going to be vec3.sub, because that is going to be our input point over here. Instead of inputting a shape with a position that is a vector 3, we're just inputting a vector 3. Size array, orientation array, that's all good. We're going to loop over the orientation array. We're going to get each axis in the orientation array. We are going to get the distance projected of the direction from the point to the OB's origin on that axis. And then instead of saying if the absolute value of the distance is greater than the absolute value of the size, we are going to say the distance is going to be clamped between, let's see, the distance is going to be clamped distance between negative size array index I and you could say plus size array index I, although I think the GameMaker like syntax checker would yell at you for that, so it's just going to be the positive size array index I like this. And the third times the charm, res ult is going to be results.add the result of the axis. So the axis of orientation, and we're going to multiply that by the distance, like this. And then instead of returning true or false, we're going to return the we're going to return the result. I'm having a lot of trouble with this word today. It's weird. If you wanted to, and I guess I'm going to have to mention this sooner or later, if you wanted to, you could just treat ABBs always as an oriented bounding box with an orientation matrix that's just like the identity matrix, the identity 3x3 matrix. But as you should be able to tell just by visually looking at the code, the math for computing a lot of things when it comes to ABBs is slightly simpler than the math for computing the same thing for OBBs, due to the fact that you can make some assumptions if the orientation is just like aligned to the coordinate system, and therefore is slightly cheaper to calculate, and that's extremely important when doing things like sorting your collision worlds into octrees or other structures such as that, if you have to do a lot of bounding box checks for a single like collision detection. But regardless, that should be everything that we need to do for nearest point. We should be able to implement the check sphere method without issue. If I were to run the game, and if I were to zoom in, let's bring up an OB, and what's a sphere? Sphere is going to be the X key. So if I were to drag you out, we have an error. Okay, that's cool. All right. I must not be fully awake today or something, because really, nearest dot distance to self dot position. That needs to be nearest dot distance to the sphere's position. Okay. I was hoping to record both this video and next week's video within like the span of today, but if I keep this up, I might want to just put that off until I'm like properly awake or something. So now If we were to move the ab around in space through the sphere, we can see that we have a collision. If we were to try another axis from another direction, we can see that we have collision or not. If I can try and pinpoint exactly where that collision happens, it's about here. We can move it through the bottom. We can move it forwards or backwards, and we have collision between the ab and the sphere, the ob and the sphere. All right. So that was ob sphere, and another very silly mistake. Let's see. We can say implemented the ob and the sphere test. All right, at the rate that I'm going today, I'm starting to feel like we're casting a little bit of doubt on whether I'll be able to get the check triangle methods for obs done today. Definitely gonna do abs and obs. I'm sorry, that sounds so ridiculous out loud. I'm definitely going to do collision detection tests for these two against the ob. If I'm really crunch for time, I might also put off plane until next time as well. The plane isn't difficult. That might be a nice, easy thing to start the next video on, if I really end up taking my time here. Next, call ob, check ab, and call ob, check ob are going to be almost identical. The only difference between them is going to be a couple lines of code. This is going to be very similar also to the check, where was it? I know it's in here somewhere. The check ab SIT example that I did in about a year ago in Act 2 when it came to demoing the SIT, checking two axis line bounding boxes against each other. When it comes to ab tests, of course, the fact that they are aligned to axes means that you can get away with doing a lot less work because you can make some assumptions, and you can literally just check to see if box.getMin is less than box.getMax and all that. But when it comes to bounding boxes that have a rotation component, that is not something that you can do, so you've got to do the full-on separated axis theorem like this. I'm going to start with call obs, check ab, and then I'm going to move on to call obs, check ob, and we're going to see how similar they are. I'm also going to do the thing that I think has burned me several times in the past, but I'm going to do it anyway. I'm going to copy the contents of check ab SAT, and I'm going to paste that into obs, check ab down here. And we're going to do something a little similar. We are going to have more axes of rotation that we can test because we do have the orientation information, and we're going to have to we're going to have to check more axes than just the the X, Y, Z like this down here. And checking two abs against each other have a total of 3 axes of separation. Checking an ob against an ab or an ob against an ob, we're going to have a total of 15. So the first 3 are going to be the same because at least in the case of the ab. The second 3 are going to be self.orientation.x, self.orientation.y, self.orientation.z. We're going to have each of the 3 axes of rotation for the ob. These 3 up here are the axes of orientation for the ab as well, but as I keep saying, being aligned to the world's coordinate system means that you can just hardcode those to these 3 values. And we're also going to have a total of 9 more axes of potential separation that we're going to be checking, and those are going to be the 3 axes of the ab cross product against the 3 axes of the ob. You could write those out the long way if you wanted to. You could say new vector 3 dot cross against self dot orientation dot x. You could say GameMaker. You could say new vector 3 100 dot cross self dot orientation dot y. You could say 100 dot cross self dot orientation dot z, or you could use a for loop. I'm going to use a for loop. That's going to make this a little prettier. Say for var I equals 0, I is less than 3, I plus plus. We're going to have to do this a total of 9 times, so 3 of these cross against 3 of these, so we're going to have a inner for loop. So for var j equals, going to make this 3, j is less than 6, j plus plus. Again, obligatory shout out to the hard-coded magic numbers. Once again, unless you are intending to extend this to 4-dimensional shapes, you should be okay. We could say array push axes index I dot cross against axes index j. And that is going to be our total of 15 axes of potential separation. Now, let's see. We're going to have to iterate over each of the 15 axes in here now. So we're going to change this for loop down here to for I equals 0, I is less than 15. And we're going to check to see if there's an overlap on an axis the same way. This is going to be just call overlap axis ourselves with regards to the AB like this. So shape 1, shape 2, and the axis of separation is going to be the this axis over here. And next we're going to need to go down to, I believe, the bottom of this code file and implement the getInterval method. This is going to be, I guess you could say it's going to be similar to the call abs getInterval in that it's going to be 8 points, which are going to be the 8 corners of the shape. And we're just going to do this whole thing to get the minimum and maximum value of each of those points on the axis in question. That's going to be somewhat like doing a nearest point calculation, but instead of checking for the nearest point on all 3 axes, we're just going to be checking for the nearest point on one axis from like the minimum and maximum points of an OB. And the 8 vertices in question of the call ob shape are going to be a little bit uglier to find than the 8 vertices of the 8 points on an AB, and that is because of the that dastardly orientation matrix that we're going to have to figure out exactly where like each of the points in space are, taking into account the orientation information. And to do that, I can write out this behemoth line of code that is going to be something like 150 characters long by the time I'm done with it. That is going to be self.position.add, self.orientation.x.multiply, self.size.x. So we're going to start with the position of the OB, and we're going to add the x component of the size vector multiplied by the x-axis of rotation. And next we're going to add self.orientation.y.mul, self.size.y, double close parentheses, and then we're going to add self.orientation.z.mul, self.size.z. And that is going to be one of our 8 points that are going to be our corners of our OB. And we're going to need to do this 8 times. You can type out every possible combination of adding and subtracting the size of the OB on each of the axes, like added to the original position. I'm not going to. I'm going to copy and paste this 7 more times. That's 7, right? I think that might have been 8. 1, 2, 3, 4, 5, 6, 7, 8. Nope. That was the correct number. And once again, you can write out every possible combination of adding these terms and subtracting these terms, or you can just sort of cheat by doing this like this alternating grid pattern of adding and subtracting. You can also, if you don't feel like doing that and having to squint at it to make sure that you put all your adds and subtracts in the right place, you can also go to the Github repository for this project down in the video description and just like copy and paste these 8, or I guess 10 lines of code to save yourself the heartache of having to write them out from scratch. Technically, you could just do that for all my code because I'm not going to stop you, but if you're the type of person who's made it 23 videos into a series on 3D collision detection, then you're probably not the type of person who just wants to copy and paste code like that. Anyway, these are our 8 vertices, and everything else in the getInterval method for an oriented bounding box is just going to be the same as getting the interval for an axis-aligned bounding box like this. You're going to basically find the minimum and maximum extents of the axis in question dot producted against each of these 8 vertices, and that is going to be your interval. And we can just do the exact same thing. So the minimum and maximum points here. If you wanted to, you could initialize I min to like positive infinity, and you could initialize I max to negative infinity, and you could instead loop over like this from I equals 0 to 8. But for some reason, initializing like minimums to infinities and maximums to negative infinities seems to be a little bit more confusing than just doing it like this, than like initializing them to the value of like index 0 and then proceeding from there. So I'm going to leave it like that. Anyway, that should be check ab. I shouldn't have to do anything more. I'm just going to do a quick once over to make sure that each of my i's and j's are in the correct places and all that, and it looks like they are. So if I were to run the game now, if I were to bring up myself an OB, and if I were to bring myself up an AB, argument 0 is not an array. Okay, possibly the silliest mistake at all, and I swear that I'm like alive today, because we've got to array push onto an actual array and not just like a non-value like this, because that doesn't make any sense. Let's see, again, bring up myself an OB and bring up myself an AB, and I can play around with the extents of the OB like this, and I can make sure that everything is overlapping where it should be and not overlapping where it shouldn't be. Right, there is a tiny axis of separation there. The axis of separation, I don't know how well I described in words exactly what an axis of separation is back when I started doing these SAT tests. But if you can imagine being able to, at any point, draw a line between two shapes, like if the side of this OB over here was a like a line in space, and if you could draw along that line, along the line with that slope, a line between these two shapes and not intersect the AB over here, then that would be an axis of separation found. I don't know if that's a better or worse explanation than whatever I gave at the beginning. But everything seems to be in order. We seem to be detecting collisions where we should and not detecting collisions where we shouldn't. And that's fine. So let's say implemented OB and AB. And we can do something similar, something very similar to the OBs check OB method. And the only difference here, the only difference that we're going to be doing for the OBs check OB method is that, one, we're going to have to update the name of the shape in question down here. So call overlap axis self OB axes index I. We're going to have to make sure that we're referencing a variable that exists in this method. And also, the first three axes of separation in this axis array is going to be, instead of hard-coding like the x, y, and z axes of the world's coordinate system, we're going to use the ob.orientation.xyz axes of the incoming ob's orientation array, and that is going to be the only change we have to make after this. After that, we've still got our own axes of rotation of our own like ob's orientation matrix. After that, we're still doing the cross product of each of these three axes against each of the other three axes. And at the bottom, we're still doing the overlap test between each of the between like ourselves and each of the 15 possible axes of separation up here. And if I were to run the game now, we should have OBs and OBs. We shouldn't have to do anything else for those. Let's see, zoom in, generate two OBs, and if I'm going to try and bring them together and try and separate them just barely on any given direction, we should have. Can I get a good look at this corner? That corner is hard, but it looks like that is the point of contact, like right over here where my mouse cursor is, and we should detect an intersection, not detect an intersection. On the other side, should be the same deal. Intersection, not intersection, if I were to bring you out that way. Perfect. All right, so that's OBs and OBs, very easy. And my recording has been going on for about an hour, it looks like. So that's probably going to be like 20-25 minutes after I edit it down. And I think 25 minutes is going to be enough, so I'm going to end this off here. So, my name is Michael. I like wizards and dragons and making games. If you want the code for this, look for the Git. Alright, I somehow messed up my repository, putting everything on a separate branch and then, like, deleting and moving around branches. Apparently messed up some things with the tag system, so I'm gonna have to sort that out later. If you want the code for this, look for the GitHub repository down in the video description. As I alluded to in the middle of this, if you're the type of person who's made it 23 videos into a series on 3D collisions, you're probably not the sort of person who just wants to download this code, but if you want to have a look at it to make sure that, your code is on, like, parity with my code, then the repository is there. If you want to contribute to the channel, look for the Patreon and all the usual places. I definitely would appreciate it if anyone wanted to contribute. Otherwise, I try to post about 2 game dev videos a week, one tutorial like this, and one Let's Make a Game, currently Bullet Hell. So if either of those things appeal to you, feel free to subscribe. Otherwise, I hope you all enjoyed that, and I will see you all later. Special thanks to Army Armbuster, DJ Gibbles, Edward Holt, GameMaker, KeyXE, Sindra Larson, Squarecrow, The Oz, and Zenith for supporting these videos. If you want to support the channel, head on over to the Patreon page down in the video description to join the fun.